All right, guys, we're going to do two parts today. The first one is biomes, and you all really need to self study your biomes. You've had it repeatedly, so I don't want to waste time going into it again, but realize that the gimme questions are often what biome has constantly cold temperatures and permanently frozen ground? And you should be able to come up with tundra. What biome has a lot of rain and is hot? You should be able to come up with tropical rainforest. There is a biome movie here that I ask that you watch. What is a biome? A biome is a large geographical area that has certain kinds of climate and has certain kinds of organisms. And no matter where you are on the planet, if that biome is that biome, you know what to expect. So whether or not you're in a California desert, an African desert, or a Mongolian desert, you know that there's going to be very little rain, that the plants that grow there are going to be small, usually low lying, that you're not going to have a lot of animals. If you know what the biome is, you can make educated guesses as to what you're going to find plant and animal wise. The biosphere is a little bit different. The biosphere is anywhere on the planet that life can exist, from the top of Everest to the bottom of the Marianas Trench. Here are your main biomes that you need to know. Make sure that you know the distinguishing characteristics of each biome. Remember, a distinguishing characteristic, if I blindfold you and describe or drop you into an area, what would you look at to know where you are? Biomes are defined by their temperature and their rainfall, and a climatograph. If you guys were in apes, you drew those. Look at the amount of precipitation, rain, and temperature as it varies by month. Realize that the temperature and the precipitation together give us the properties or the distinguishing characteristics of your biome. Again, we can look at our biomes both latitude and elevation. They're going to differ the same. So as you start at the poles and go towards the equator, you're going to find snow, ice, tundra, boreal, chaparral, desert, and desert, or a tropical rainforest, depending on the amount of rain you're getting. As you go up in elevation, think about going from Palm Springs to Big Bear. You leave the desert, you go through the chaparral to a boreal to tundra to above the tree line with snow and ice. All right, make sure you know your biome's, not going to spend time on it. What I do want to spend time on is this population ecology idea. Some things that affect populations with their gnarly scientific terms. Natality is just birth rate. So as natality increases, so does population. Mortality is death rate. As death rate increases, population decreases. Immigration with an I is moving in. Immigration with an E is moving out. And you look at our 10 most populated countries as of 2015, really hasn't changed much, and we don't expect it to change much. The sigmoid growth curve, you guys were taught as if it were a logistic growth curve in freshman bio. In apes, it was an S curve because it kind of looks like an S. You do need to know the points. So when we first introduce organisms into an area, we have very slow, low growth as they're getting used to the area and to each other. Then we have a period of exponential growth where the resources are in abundant supply and our population is still low enough that it's not taxing the environment. Eventually, we hit carrying capacity. Carrying capacity is the maximum number of individuals that a population can hold based on limited resources. So when you pop above carrying capacity, all of a sudden there's not enough food, or there's not enough territory, or there's not enough water. If you pop above carrying capacity, you have die-off, and you come back down to this carrying capacity area. Carrying capacity is on average. In any given year, you could be above or below carrying capacity, but if you look at a 10-year period, you're going to be on this line if you average it out. Exponential growth is the other type of population growth, but we don't really see it. Some species that do exponential growth will have a large period of exponential growth and then mass die-off, and then exponential growth and then mass die-off. They never kind of hit this carrying capacity. Bacteria are really the only things that come to mind when I talk about exponential growth. Everyone else is on a sigmoid growth curve. We talked about this already, but let's put names to it. Exponential growth, unlimited population, no limiting factors, tons of food, tons of water, tons of space. Transitional period, our growth begins to slow, and we start to have individuals no longer thriving, no longer reproducing at max rates, because all of a sudden things start to be limited. We start to see it's harder to find food, and because you're spending so much more time finding food, you're not reproducing as much. And then the plateau is carrying capacity. Limiting factor. You could have a lot of limiting factors in your life. If you think about humans, our limiting factors are food, water, shelter. But the one that truly is the limiting factor is the one that's going to kill you first. And so if food, water, and shelter are all in limited supply, the limiting factor is actually water, because you will die first because of a lack of water before you will die of a lack of food. Top-down control of carrying capacity is where predators are limiting the population. And so if there's a ton of bunnies, the coyotes will come in and keep the bunny population in check by eating them. Bottom up means that nutrients are limiting growth. And so we often think about plants and their limiting factors being a lack of nitrogen or phosphate. Factors that limit animal populations tend to be food, parasites, disease, predation, and nesting sites. If you think about these birds, they each want their own piece of the rock. And if Buddy flies in late and all of these rocks are taken, he doesn't get to have babies that year. So that's how nesting sites become a limiting factor for an animal population. For plant populations, it's the amount of light, the temperature, carbon dioxide, and water availability. Two types of strategies for living your life are strategists. These guys are your insects of the world. They go out, they pepper the environment with tons of offspring. There's no maternal care. So mama spider has 1 million babies, leaves them to themselves, mostly because she dies, because she's invested all of her energy in having 1 million babies. So she croaks, the babies are on their own. And of those 1 million babies, maybe 100 survive to adulthood. And then that 100 has 1 million babies. They have really short lifespans and they reproduce relatively quickly. These guys thrive in environments that are unstable and constantly changing. Contrast this to a K strategist. These guys are investing resources, ensuring their young are going to survive. You all are K strategists. Mom and dad had you. They didn't have a lot of you. You don't tend to have a ton of siblings, and they are investing all of their energy into making sure that you make it to adulthood. Sometimes they ensure that you make it past adulthood. You guys live for a long time, lots of parent involvement, very few offspring, and it takes you a long time to get to reproductive age. So for humans, you hit reproductive age around 13, 14. Again, you guys are examples. Elephants and whales are other examples. These guys need a stable environment because it takes so long to mature and then to reproduce again. So our strategists are in unpredictable, unstable environments. They're the cockroaches of the world. K strategists are in stable, predictable environments, and they compete for resources, but they really want things to be happy and good. If we go into an environment and there's a lot of R strategists, we know that environment is often disturbed, that the ecology of that environment isn't stable. One of the ways that we're going to estimate a population that moves, right? If you're talking about a population of trees, I can go out and count a population of trees. If you're talking a population of dandelions, I can use quadrant sampling and get the population of dandelions. But if I want to get the population of rats on campus, it's going to be a little harder because they're going to run away. They're not going to be visible. And so I want to do this thing called catch, mark, and recapture. To do that, I capture in 10, 15, 20 rats. I capture in a portion of the population. And I do so in a way that doesn't entice them, that doesn't scare them, and that doesn't harm them, because I want these things to be alive and happy and live a normal, happy rat life. When I've got them, I'm going to mark them, and I'm going to mark them in a way that doesn't traumatize them, doesn't injure them, and for the most part is not permanent. Then I'm going to release them into the environment, let them do their ratty things, and come back at a later date. Capture in a portion of my population and do some math when I look at how many that I recaptured are marked versus unmarked. That math gives you an estimate of the population. It's not perfect. It's just that. It's an estimate. And there are a lot of things that can throw your estimate off. And I'm going to ask you to think about those, and I'm going to quiz you on it later. Make sure you watch these 2 videos on how you do it. Here's the math. I'm not going to go over the math because you're going to do a lab, but you do need to memorize this equation and know how to work it. Remember I said I'm going to ask you later, what are some of the things that affect whether or not this is accurate? Here are the list of things. One of the ways that we use this Lincoln Index's catch, mark, recapture is in estimating commercial fish stocks. We do that so that we don't have overfishing. And so we're going to estimate the population of a species of fish and figure out the carrying capacity, and then say, you know what, we can catch a portion of the carrying capacity, ensuring that there'll be fish in the ocean to catch next year. And this is scientists doing that. If you want to be a biologist or a marine ecologist, one of the jobs you can get is to be on a boat and doing population estimates, and then ensuring that what the fishermen are catching is of the proper size, proper gender, proper species. Maximum sustainable yield is that number as far as what can we catch before we decimate the population. Theory of knowledge moment, because we have to have some theory of knowledge. We haven't had a lot of it this year. How should the fish stock be managed? If there's a very limited data on the world's population, and if the data is just an estimate, what do we know about the quotas that we put out? We should really err on the side of the fish. We should err on the fact that this is a fallible method, and that we should leave for sure enough fish that that population can continue. The International Conservation of Fish, we have quotas for what you can take, and we've talked a little bit about how those quotas are designed. We have aquaculture. So now instead of going out and getting Atlantic salmon or Pacific salmon and damaging the natural salmon, we will actually harvest eggs and grow those eggs in a pond, and that's what we're going to sell. And so the wild fish are left unharmed. This is kind of like having the farms for cows. We're going to have it for fish, and we leave the wild animals be. That's all we're going to talk about before we talk about the conservation of biodiversity. So yes, done. Lecture over.